pthread locks. So let's continue with thread library, just like we discussed in the previous video. The name that POSIX library uses for a lock is mutex, as it is used to provide mutual exclusion between threads. Like if one thread is in the critical section, it excludes the others from entering until it has completed the section. So that's the reason why we keep creating this lock via pthread underscore mutex. And here's example code. So we have a lock first and then unlock at the end. You might also, so this pattern will be recurrent along when discussing building a lock, evaluating a lock, controlling interrupts, using load and stores, test and set, and even in the OS implementation of threads, because it's such a fundamental with concurrency. You might also notice here that the POSIX version passes a variable to lock and unlock, as we may be using different locks to protect different variables. So we pass a variable here, we call it lock, but we can define that using a different name. That's how we create different lock and unlock pthread locks, because that's essential as well to be able to create or differentiate different locks. So that variable and or different naming of variable is essential for organization. Doing so can increase concurrency. Instead of one big lock variable that is used anytime any critical section is accessed, which is a coarse grain locking strategy, one will often protect different data and data structures with different locks, thus allowing more threads to be in lock code at once. A more fine-grained approach. So these are more fine-grained or more detailed, because it encompasses not just the whole lock strategy, but also the different data, specific data and data structures that our code is running. Building a lock, so or the crux, how to build a lock. How can we build an efficient lock? Efficient locks provide a mutual exclusion at low cost and also might attain a few other properties we discussed below. What hardware support is needed and what OS support. So we will start with what kind of hardware support did the providers provide us along the years. So we're gonna study the history on how the hardware was implemented to be able to support lock library. As we will see, this is just a code for supporting those instruction or enabling those hardware features, because again, no one writes assembly code anymore. Usually, even for this hardware instruction, we are using C code. So over the years, a number of different hardware primitives have been added to the instruction sets of various computer architectures. So another thing is that these are actually more about the code that allow us to create this library to be able to communicate to these different architectures that have been developed throughout the years. But it's not the detailed way on how the CPU works. So I would recommend you like reading architectures book. So there's some book, a good book for architectures. Let me check this. Inside the Machine. So that's a good book that allows us to understand the computer architecture. We will study how to use them in order to build a mutual exclusion primitive like a clock. We will also study how the OS gets involved to complete the picture and enable us to build a sophisticated locking library. So the OS will complete the picture. So that's the key. Hardware will provide the necessary, like the foundations, and then we will just use the OS to complete its feature to be able to fix some of its downside along the way. Evaluating locks. Before building any locks, we should first understand what our goals are, and thus uh, we ask how to evaluate the efficacy of a particular lock implementation. The first is whether the lock does its basic task, which is to provide mutual exclusion. Basically, does the lock work, preventing multiple threads from entering a critical section? So before building any C code that allow us to take advantage of this hardware feature that has been developed throughout the years, we need to be able to know what our goal with this C code we're gonna be using to support thread library. Of course, the first criteria would be, does it actually work? Does it provide what we intended to do, which is the mutual exclusion? The second is fairness. Does each thread contending for the lock get a fair shot at acquiring once it's free? Another way to look at this is by examining the more extreme case. Does any thread contending for the lock starve while doing so, thus never obtaining it? The final criterion is performance, specifically the time overheads added by using the lock. There are a few different cases that are worth considering here. One is the case of no contention, when a single thread is running and grabs and releases the lock. What is the overhead of doing so? Another is the case where multiple threads are contending for the lock. Finally, how does the lock perform when there are multiple CPUs involved and the threads on each contending for the lock? By comparing these different scenarios, we can better understand the performance impact of using various locking techniques as described below. Again, the final criterion is performance, specifically the time overheads. So the time, not really the space. There are a few different cases that are worth considering here. One is the case of no contention, when a single thread is running and grabs and releases the lock. Controlling interrupts. One of the earliest solutions to provide mutual exclusion was to disable interrupts for critical section. This solution was invented for single processor system. So here, void lock. So again, void are used for multiple types or many types of data to be returned to. So void lock function inside this is disable interrupts, and then void unlock enable interrupts. Then closing semi curly bracket. By turning off interrupts using some kind of special hardware instruction before entering a critical section, we ensure that the code inside the critical section will not be interrupted, and thus will execute as if it were atomic. So if we disable the interrupt, therefore, the code while running in that shared data will provide mutual exclusion, all or will not be interrupted. Thus will execute as if it were atomic. When we are finished, we re-enable interrupts again via hardware instruction, and thus the program proceeds as usual. So when we are finished, we simply enable that via hardware instruction. So like this code, this is how we do that. This is how we wake up or allow or re-enable that thread via hardware instruction. This is the code, the void lock, and then disable interrupt, and void and lock enable interrupts. The negatives, unfortunately, on this strategy are many. First, this approach requires us to allow any calling threads to perform a privileged operation, turning interrupts on and off, and thus trust that this facility is not abused. As you already know, anytime we are required to trust an arbitrary program, we are probably in trouble. Here, the trouble manifests in numerous ways. A greedy program could call lock at the beginning of its execution and thus monopolize the processor. So a greedy thread, a program with a thread could call this lock code for our thread library at the beginning and monopolize the entire processor. Worst, an errant or malicious program could call lock and go into an endless loop. In this latter case, the OS never regains control of the system, and there is only one recourse: restart the system. Second, the approach does not work in multiprocessors. If multiple threads are running on different CPUs and each try to enter the same critical section, it does not matter whether interrupts are disabled, threads will be able to run on other processors and thus could enter the critical section. So basically, since that data is in memory somewhere, if you have a multiprocessors, therefore multiple processor would access that data. So this only work on single processors, and thus could enter that critical section or shared data from memory or disk. Third, turning off interrupts for extended periods of time can lead to interrupts becoming lost, which can lead to serious system problems. So imagine, for example, if the CPU missed the fact that a disk device has finished a read request, how will the OS know to wake the process waiting for said read? So because of the VAG that this interrupt or disabled interrupt cause, such as turning off like for endless loop, therefore turning it off for a long period of time, therefore disabling the wake up, because this interrupt is actually what allows the conditional cond we discussed in the previous video, the one waking and sleeping the threads. These are actually the same time slice or the same hardware support that we use to be able to confirm with the program that they were able to read something from the disk or from the memory. So for these reasons, turning off interrupt is only used in limited contexts as a mutual exclusion primitive. For example, in some cases, an operating system itself will use interrupt masking to guarantee atomicity when accessing its own data structures. So it's worth it to go back to here in performance because it's kind of abstract. So basically, for performance, we have we have three goals: mutual exclusion, fairness, and performance. For performance, we want to try to reduce overhead despite using this lock. So there are three edge cases that worth considering, or things that is realistic to be a problem with our systems based on the knowledge we know thus far. So first is that we analyzed what happened if a single thread is running and releases the lock. What if only one thread is using that shared critical section without contention? What are the performance of doing so? Another case where multiple threads are containing for the same shared data on a single CPU. In this case, there are three. Are there performance concerns? Finally, how does the lock perform when there are multiple CPUs involved and threads on each contending for the lock? So what if you have thread in different CPUs containing for the same lock? How would be able to maintain performance despite those edge or cases? By comparing these different scenarios, we can better understand the performance. So we will be able to better understand or know more about the performance impact of using various locking techniques that we are describing, such as this controlling interrupts, etc. So here, this type of disabling interrupts are actually useful in operating system because there's no trust issues that other program could take over and like do an endless loop when accessing its own data structure, because some of its function of kernel is actually just needs atomicity for its own code and data structure. So to be able to understand more on how we can better or how can we achieve our goal of fairness, performance, and mutual exclusion, it's worthy to check what are the failed approach in the past, or at least try to solve the problem using load and stores. You know what we currently know about the hardware, or what what hardware available feature that time is available to solve our problem. To move beyond interrupt based techniques, we will have to rely on CPU hardware and the instructions it provides us to build a proper lock. So the CPU already provides us these loads and stores. So in this failed attempt, we'll see some of the basic ideas needed to build a lock, and hopefully see why just using a single variable and accessing it via normal loads and stores is insufficient. So we will see why a single variable in a lock, so just like our lock have different names, right? So using a single, what if we use a single variable? What are the pros and cons? And also using the existing hardware, CPU hardware features such as normal loads and store, how does it actually work? Can we actually achieve our goal with existing hardware features? So in this first attempt, figure 28.1, the idea is quite simple. Use a simple variable flag, here mutex flag, to indicate whether some thread has possession of lock. So again, mutex allow us to create a mutual exclusion. So here we use the flag. The first thread that enters the critical section will call lock, which is this void lock again. So again, we use void lock because we want to accept many types of many different types of data, and hopefully we'll call lock, which tests whether the flag is equal to 1. So because these are the code is structure, so we initialize lock t mutex with a variable flag when it is equals to 0, meaning lock is available, so 1 will hold. So here we define the structure lock t int flag. So that's how we define the one variable. So the first thread that enters critical section will call lock, here lock underscore t mutex, which tests whether the flag is equal to 1. So while mutex flag equals to 1, or test the flag. In this case it is not, and then sets the flag to 1 to indicate that the thread now holds the lock. So in this case it's not, since it's 0, initially 0, then it sets it to 1 to indicate that the thread now holds the lock. When finished with the critical section, so after this, the thread calls unlock and clears the flag, thus indicating that the lock is no longer held. So after you're done, you test the flag, or after you set it to 1, you called unlock. So this line of code, and then while mutex flag equals to 1 and mutex flag equal to 1, did a lot of things, just like the previous one line of code we discussed in the previous video. So it's amazing how one line of code allow us to create many things or many different actions at once. So if another thread happens to call lock while that first thread is in the critical section, it will simply spin wait in the while loop for that thread to call unlock. So again, if another thread happens to call lock while that first thread is in the critical section, it will simply spin wait in the while loop. So if it's not yet finished in this critical section, the first thread, since it's equal to 1, the other thread will just spin wait in this while loop for the thread to call unlock. And clear the flag. So it will spin wait for the other thread to call unlock and release the flag. Once the first thread does so, the waiting thread will fall out the while loop. So it will fall out this spin after this spin wait and set the flag to 1, mutex flag to 1 for itself, and proceed into the critical section. After done accessing that critical section, whatever you have data you have that there or function you have will execute, and then after that we'll call void unlock to release the flag. So unfortunately, the code has two problems, one of correctness and another of performance. As you can see, so that are the two goals that it didn't achieve. So as you can see from the interleaving with timely and untimely interrupts, so if it's the interrupts is untimely, we can easily produce a case where both threads set the flag to 1 and both threads are thus able to enter the critical section. So here, thread 1 call lock while flag is equals to 1. So while it's running this while flag equals to 1 line of code, it was interrupted, switch to thread 2. It called flag again, and while flag equals to 1, it set the flag to 1. It was now interrupted again by thread 1. It set the flag to 1. So set flag to 1 too. So this behavior is what a professional calls bad. So we all have obviously failed to provide the most basic requirements, providing mutual exclusion. The performance problem, which we will address more later on, is the fact that the way a thread waits to acquire a lock that is already held. It endlessly checks the value of a plug. So because it's spin weight, it endlessly checks the value of a plug. Therefore, if that critical section or that function in that critical section took too long to load, therefore the other thread will also need to wait for that specified time, therefore decrease the performance. So it endlessly checks the flag, a technique known as spin waiting. So spin waiting wastes time for another thread to release a lock. The waste is exceptionally high on uniprocessor or one processor, where the thread that the waiter is waiting for cannot even run, at least until a context switch occurs. So until a context switch. So one of the takeaways here is that uh, the other thread or other process, just like in modern operating system, could be could use the or could disrupt the other process by just clicking the other app, such as clicking Google Chrome, clicking OneNote, or clicking Word. So you can easily disrupt that process. So aside Dekkers and Peterson algorithms, in 1950s, Dijkstra posed the concurrency problem to his friends, and one of them, a mathematician named Theodorus Joseph Dekker, came up with a solution. So unlike the solution we discussed here, which uses special hardware instructions and even OS support, Dekker's algorithm uses just loads and stores, so the basic hardware support, without just like this hardware support like the thread which is mutex. Okay, it already have the mutex. It just use the flag as a single variable and the load and store. So it can actually solve by this, but it is not as efficient with the modern hardware. So unlike the solution we discussed here, which uses a special hardware instructions, which we will discuss later, and even OS support, Dekker's algorithm uses just loads and stores, assuming they're atomic with respect to each other, which was true on early hardware. Dekker's approach was later refined by Peterson. Once again, just loads and stores are used, and the idea is to ensure that two threads never enter a critical section at the same time. Here is Peterson's algorithm for two threads. See if you can understand the code. What are the flag and turn variables used for? So it defines flag, int flag, with two argument, open and close square bracket, and then it defined int turn, semicolon, and then void int function again. Inside, it indicate you intend to hold the lock with flag. So flag argument 0 equals to flag argument 1 equals to 0. And then next line was turn is it question mark thread 0 or 1. So turn equals 0 semicolon close semi-curly bracket void lock. Inside self is the thread ID of caller. Flag self equals to 1. So flag with the argument self equal to 1, and then make it other threads turn. Turn equals to 1 minus self, while flag argument 1 minus self equals to 1, and turn equal to 1 minus self, semicolon spin wait, it's not your turn, closing semi-curly bracket void unlock, simply undo your intent. Flag self equals to 0. So for some reason, developing locks that work without the special hardware support became all the rage for a while, giving theory types a lot of problems to work on. Of course, this line of work became quite useless when people realized it is much easier to assume a little hardware support, and indeed that support had been around from the earliest days of multiprocessing. Further algorithms like the ones above don't work on modern hardware due to relaxed memory consistency models, thus making them even less useful than they were before, yet more research relegated to the dustbin of history. So tip, think about concurrency as a malicious scheduler. So these are one of the techniques that allow us to understand concurrency. From this example, you might get a sense of the approach you need to take understand concurrent execution. What you should try to do is to pretend you're a malicious scheduler, one that interrupts threads at the most inopportune of times, because that's what happens all the time with apps. Suddenly you switch or you context switch, therefore stop the other thread in order to foil their feeble attempts at building synchronization primitives. So what a mean scheduler you are. Although the exact sequence of interrupts may be improbable, it is possible. So though different type of sequence could happen in the real world implementation, though it's improbable, it's possible. So you need to prepare for that edge cases. And that is all we need to demonstrate that a particular approach does not work. So it can be useful to think maliciously at least sometimes, because you're preparing for a worst case scenario or edge cases. That's the reason why it can be useful to think maliciously, because you're being realistic and preparing for the worst case, or thinking yourself as a malicious scheduler. So building spin locks with tests and sets. So because interrupts, so these are the first hardware support we will be explaining. So because interrupts and simple approaches of loads and stores, such as the flags shown above, are not enough, system designers start to invent hardware supports for locking. The earliest multiprocessors, such as Boros B5000 in the early 1960s, had such support. Today, all systems provide this type of support, even for a single CPU system. So the simplest bit of hardware support to understand is known as test and set. So these are the simplest hardware support, or atomic exchange instruction. So it's actually atomic exchange instruction. So we define what test and set instruction does via the following code snippet. So int, so again we used int again, test and set. Argument int asterisk old underscore pointer comma int new. Inside int old equal asterisk old underscore ptr semicolon, which mean fetch old value at old underscore ptr. So we get the value from the old pointer. Old underscore asterisk, and then next line asterisk old underscore ptr equals to new semicolon, store, which means store new into old underscore ptr, and then return old semicolon, return old value. So these are the simple spin lock test and set library to be able to support that lock library primitives. So type def struct underscore lock t, inside int flag, closing curly semi bracket, lock t semicolon. Now we initialize again like the one before, void init lock, void init with an argument lock underscore t asterisk lock. Inside it is lock to flag equals to 0, which means lock 0 lock is available, 1 lock is held. Void lock, and then after that function, we define void lock function with an argument lock underscore t asterisk lock. Inside, while test and set log to flag 1 equals to 1, spin wait do nothing, and then close semi curly bracket. So and then next function is void unlock with an argument lock underscore t asterisk lock, with inside this is lock to flag equals to 0 semicolon close semi curling bracket. So that's a simple lock using test and set to be able to create that lock functionality with the library to support the hardware, with the support of hardware. So what the test and set instruction does is is follows. It returns the value pointed to by the old pointer and simultaneously updates said value to new. So that's how it achieves atomicity. It returns old value pointed by the pointer, so the value it will return the value instead of the address, and simultaneously updates the value to new. After it return it, it saves the old, simultaneously update to new. The key of course is that this sequence of operations is performed atomically supported by the hardware by defining that via int earlier. So the int old and then old equals to new, etc. So the reason it is called test and set is that it enables you to test the old value, which is what is returned, while simultaneously setting the memory location to a new value. So while simultaneously setting the memory location or the address to a new value. This slightly more powerful instruction is enough to build a simple spin lock that support the spin lock we described earlier using just a basic load and store and flag. So because of that, it actually allow us to, because we activate this feature of hardware, so we actually allow to use the previous like concept of flag with a little bit support of hardware to enable this atomicity. So imagine first the case where a thread calls lock. So let's say a function or a thread calls this lock function of the library and no other thread currently holds the lock. Thus flag should be 0. When the thread calls test and set here, flag 1. So let's imagine the first case where a thread calls lock and no other thread holds the lock for this library. So the thread will call this test and set that has been defined with the support of hardware. The routine or the library will return the old value of flag, which is 0. Thus the calling thread, which is testing the value of flag, will not get caught spinning in the while loop. So it will not get spinning in this while loop, just like the one we have earlier with the simple flag variable and activation of load and store, and will acquire the lock, and it will actually acquire the lock and then enter that critical section. The thread will also atomically set the value to 1. So here, so aside from that, this line of code actually set the value to 1. So it avoids spinning. This code will avoid spinning, while at the same time will return the value of flag, which is 0, which came from the hardware code and hardware support, which we defined via int earlier. And it actually simultaneously acquired the lock. So that's the key, this simultaneous behavior, because of that initialization within hardware support in a separate class in this library. So the thread will also automatically set the value to 1, thus indicating that the lock is now held. So the thread will also automatically set the value to 1 like this, thus indicating that the lock is now held. When the thread is finished with its critical section, so it will set the value to 1 because that's what the hardware support does with this test and set, and thus indicating that the lock is now held. When the thread is finished with its critical section, it calls unlock to set the flag back to 0, so that making it available for other threads. So the second case we can imagine arises when one thread already has the lock held, like flag is 1. So in this case, this thread will call lock and then call test and set flag 1 as well. So there's two action if there that one thread already holds the flag. it will call the lock and will call the test and set, provided by the hardware routine. Hardware int um, class. So in this abstraction class, this time test and set will return the old value at flag, which is 1. So because that's the hardware code, it will return the old, because that's another thread is currently in the critical section because the lock is held, while simultaneously setting it 1 again. So it returned the 1 while simultaneously setting it to 1. As long as the lock is held by another thread, test and set will repeatedly return 1. So this code, means a lot in different edge cases. While test and set and lock to flag 1, then equals to 1. And thus thread will spin and spin until lock is finally released. So it will spin and spin and wait for that thread to release that flag until it releases. So when the flag is finally set to 0 by some other thread, the thread will call test and set again. So again, it spin and spin, it call and call the test and set over and over again, which will now return 0 because the other thread that holding it, release it, setting the which will now return 0 while automatically setting the value to 1. So which will now, the test and set will return the old value 0 and then set the value to 1 and then acquire the lock and enter the critical section and execute the function there. So by making both the test of the old lock value and set of the new value a single atomic operation, we ensure that only one thread acquires the lock. So by making both the test of the old value by returning it, so that's actually another, two views or two functions of that, returning it and also testing it, and set of the new value, so a single atomic operation, setting it as a new value, we ensure that only one thread acquires the lock, and that's how to build working mutual exclusion primitive with the help of the hardware and with the creation of this thread function that allows for program threads to call via lock. So you may also now understand why this type of lock is usually referred to as a spin lock. It is the simplest type of lock to build, and simply spins using CPU cycles until the lock becomes available. This is also its weakness, because it spin and spin and spin until it call the test and set again. So to work correctly on a single processor, it requires a preemptive scheduler to work correctly, because you need to be able to interrupt this. Otherwise, if you had some bug with that critical section and it runs forever, those waiting thread will also run forever. So preemptive scheduler, one that will interrupt a thread via a timer. So that's what a preemptive scheduler, a one that will interrupt a running thread via a timer in order to run a different thread from time to time. So a one that will interrupt the thread from entering that critical section, getting it out in order to run a different thread there from time to time. So without preemption, spin locks don't make much sense on a single CPU, as threads spinning on a CPU will never relinquish it. So evaluating spin locks, the most important aspect of lock is correctness. Does it provide mutual exclusion? The answer here is yes. The spin lock only allows single threads to enter the critical section at a time. Thus, we have a correct lock. Spin lock don't provide any fairness guarantees, because the one thread could spin and spin and spin. Indeed, a thread spinning may spin forever under contention. Simple spin locks, as discussed thus far, are not fair and may lead to starvation. The final axis is performance. What are the costs of using a spin lock? To analyze this more carefully, we suggest thinking about a few different cases. In the first, imagine threads competing for the lock on a single processor. In the second, consider threads spread out across many CPUs. So for spin locks in the single CPU case, performance overheads can be quite painful. So this is not good for one or a single processor, but since there's already a multiprocessor today, it can be applied in the right way. So here for a single processor, imagine the case where the thread holding the locks is preempted within a critical section. The scheduler might then run every other thread. Imagine there are n minus 1 others, each of which tries to acquire the lock. In this case, each of those threads will spin for the duration of a time slice before giving up the CPU. So imagine a thread running in critical section will be stopped, via timer interrupt using preemptive scheduler. And imagine you have like a lot of thread waiting, spinning just for to get some cycles of that CPU, because you have a single processor. All of that will wait and waste a lot of waiting time for those threads. And it will spin for the duration of a time slice before giving up the CPU. So those threads that's waiting are will spin for the duration of time slice of this interrupt before giving up the CPU. So a waste of CPU cycles. However, on multiple CPUs, spin lock works reasonably well. If the number of threads roughly equal the number of CPUs, the thinking goes on as follows. So imagine thread A on CPU 1, thread B on CPU 2, both contending for a lock. So if a thread A, CPU 1 grabs the lock, and then thread B tries to, B will spin on CPU 2. So here, if the thread is running on CPU 1, if thread A is running on CPU 1, and then thread B tries to, instead of running on CPU 1, it will spin on CPU 2, therefore serving there both serving both the thread instead of waiting CPU or spinning cycle just to wait for that thread to finish executing that critical section. However, presumably the critical section is short, and thus soon the lock becomes available and is acquired by thread B. So instead of that, spending CPU cycle in just one processor waiting for that thread to finish, for that thread to finish with that lock or share the critical section, it will run instead on CPU 2. But that presumes that the critical section is short, and thus the lock becomes available later or immediately after in the processor 2. Spinning to wait for a lock held on another processor's doesn't waste many cycles in this case, and thus can be effective. So spinning to wait for a lock held on another processor. So if you're spinning to wait for that lock, special lock key to enter that critical section on another processor, doesn't waste as much CPU cycle as in one processor. So another hardware support is compare and swap. So another hardware primitive that some systems can provide is known as compare and swap instruction, and it is called on SPARC, for example, or compare and exchange as it is called on x86. So the C pseudocode for this single instruction is found in figure 28.4. So here in compare and swap, argument int asterisk ptr, comma int expected, comma int new. So here inside it, int original equals to asterisk ptr, and then we have if else statement instead of just a variable equating others to new, from old to new, and from new to old, like just like the test and set. So here we have an if argument original equal expected, asterisk next line asterisk ptr equals to new semicolon, next line return original semicolon, close curly semi curly brackets. So the basic idea for compare and swap to test is for sorry, the basic idea is for compare and swap to test whether the value at the address specified by the PTR is equal to expected. Thus compare. If so, update so if the value at the address specified by PTR is equal to expected, here PTR and expected, update the memory location pointed to by PTR. So update the value with the new value pointed to by PTR. If not, do nothing. So here PTR is equals to new. If not, return original. In either case, so if original is equals to expected, asterisk PTR equals to new. So that's what it meant by if so, update the new memory location pointed to by the PTR with the new value. So int original equals to asterisk PTR. If not, do nothing. So that's what if not, do nothing is about. So in either case, they return the original value at the memory location, thus allowing the code calling compare and swap to know whether it succeed or not. So in other case, since it will return the original value, the thread that calls it allows to know whether it succeed or not. So with this, with the compare and swap instruction, we can build a lock in a manner quite similar to that with the test and set. For example, we could just replace the lock routine above with the following. So void lock, argument lock underscore t asterisk lock inside it, while compare and swap lock to flag 0, 1 equals to 1. So and then closing semi-curly in the rest of is the same as test and set. So the rest of the code is the same as test and set example above. This code works quite similarly. It simply checks if the flag is 0, and if so, atomically swap in a 1, thus acquiring the lock. So it's the same. So thread it checks if it's 0, and if it does, it acquire the lock because no threads are using it. So threads that try to acquire the lock while it is held will get stuck spinning until the lock is finally released, just like the test and set. Finally, as you may have sensed, compare and swap is more powerful instruction than test and set. We will make some use of this power in the future when we briefly delve into topics such as lock-free synchronization. However, if we just build a simple lock with it, its behavior is identical to spin lock we analyzed above. So these are hardware features that could promote a better, like a more powerful capability with more sophisticated code such as lock-free synchronization. But with just a simple lock we created, it's the same power with the test and lock. So load, link, and store conditional. So some platforms provide a pair of instructions that work in concert to help build critical sections. On the MIPS architecture, for example, the load, link, and store conditional instructions can be used in tandem to build locks and other concurrent structures. So here, for on MIPS architecture for our processor, these are the code to initialize it. So instead of test and swap or compare and swap, int load link with an argument int asterisk pointer. Inside this return asterisk pointer, and then int store conditional with an argument int asterisk pointer comma int value. Inside it, if, so it has an if else, just like a compare swap. If no update to asterisk pointer since ll to this address, inside this asterisk ptr equals to value semicolon, next line of code return 1 semicolon success, then closing semi curly bracket else return 0 semicolon failed to update. So these are load, link, and store conditional. So as you can see, guys, the PTR are actually some of the ways for us to activate the hardware. So those are the code that are provided to by the hardware. Just like in compare swap, which we use like PTR as well, but expected and new are used just like in test and set. Here we use value as this PTR equals to value, and then we also use return. If and return is also ways for us to communicate with the or to activate hardware related features. So for example, the load, link, and store conditional instruction can be used in tandem to build lock and concurrent structures. So these hardware features can also use to build lock library and concurrent structure. So the C pseudocode for this instruction is shown here, which we discussed. So the load link operates much like a typical load instruction and simply fetches a value from memory and places it in register. So here, int load link with an argument int asterisk ptr, inside this is return asterisk ptr, simply fetches a value from memory. So it gets a value from memory and then places it in a register. So it's like this code are transferring data from memory and actually putting that in the CPU register. So the key difference comes with the store conditional, which only succeeds and update the value using if else and updates the value stored at the address, which only succeeds and update the value stored at the address. Just load link from if no intervening store to the address has taken place. So this store conditional only succeeds and update the value stored at that address or at that register, from memory. Just load link from if no intervening store. So if no update to asterisk ptr since ll to this address, if there's no recent address change has taken place. So that's the store conditional. In the case of success, the store conditional return 1. So if no update to ptr on this register, asterisk ptr is equals to value return 1 success. So if in the case of success, the store conditional returns 1 and the updates the value at ptr to value. So it updates the ptr to value. So this ptr, these are the int or the argument in store conditional hardware communication from the OS code. So if it fails, the value at ptr is not updated and 0 is returned. So as you can see, else return 0 failed to update. Now the lock code is the only interesting piece. So first, a thread spins waiting. So here we use a void lock. So it's still we only change the void lock part. First, so these are the code for the void lock when a thread are using it to call this thread library. So void lock argument lock underscore t asterisk lock. Inside this is while 1. Inside this is while load link and lock to flag equals to 1. Next line, spin until it's 0. So if store conditional lock to flag 1 equals to 1, return if set to 1 was success, done. Otherwise, try again. then close semi-curly bracket, and then close, and then void and lock. Still the same void and lock code. So the lock code is the only first a thread spins waiting for the plug to be set. So these are the code. Void lock while one. So first a thread spins waiting for a plug to be set to 0 and thus indicate the lock is not held. So once the thread called this, it will wait until it's 0. So these are the code. While 1, while load link flag equals to 1, spin until it's 0. Because, of course, if it's 1, another thread is using it. Or another, what you call this? Yeah, another code is using it. So that's the first or load link part. Now, once so, the thread tries to acquire the lock via the store conditional. So the store conditional is like kind of activating that hardware part. If store conditional lock flag 1 equals to 1, return. If set to 1 was success, done. So once it's 0, the thread tries to acquire the lock via the score. So this is how it acquires the lock once it's 0 via store conditional. So if it succeeds, the thread has automatically changed the flag value to 1 and thus can proceed into critical section. So again, if it succeeds, once so, the thread tries to acquire the lock via store conditional. So if it succeeds, which means that there's no recent changes, the thread has automatically changed the flag value to 1. So if store conditional lock flag 1 equals to 1, return. If set to 1 was success, done. Because again, no recent change. Note how failure of the store conditional might arise. One thread calls lock and executes the load link, returning 0 as the lock is not held. So yeah, here if store conditional lock to flag 1 equals to 1, return. If set to 1 was success, done. Otherwise, it will just try again. So if it succeed, then good. We just updated to 1. But note how the failure of the store conditional might arise. So one thread calls lock and execute the load link, returning 0 as the link is not held. So before it can attempt the store conditional, it is interrupted and another thread enters the lock code. Also executing the load link instruction and also getting 0 and continuing. At this point, two threads have each executed the load link and each about to attempt the store conditional. The key feature of this instruction is only one of these thread will succeed in updating the flag to 1. So this what it does is, because if a failure like this load link, accept the true thread request, but in this store conditional, this is actually where the actual test is, because for example, in two seemingly same time, both threads access or try to acquire one. So one thread calls lock and executes the load link, returning 0 as the lock is not held. So before it can attempt the store conditional, it is interrupted, because again, we're trying to fix that interruption time, like one, for example, in the simple load and store and flag variable, where some interrupt it and therefore it avoids the synchronization. Here, even you interrupt it, so let's say before it can attempt the store conditional, it is interrupted and another thread enters the lock code, also executing the loading instruction and also getting a 0 and continuing. So both has 0 now. At this point, two threads have each executed the load link and each are about to attempt the store conditional. The key feature of these instructions or hardware support is that only one of these threads will succeed in updating because of this if else, if no recent change, right? So therefore, that recent change will only update it to one if no other previous thread uh, access it, or like no thread held it before that other thread interrupts it. So only one of these thread will succeed in updating the flag to one and thus acquire the lock. The second thread um, the second thread to attempt to store conditional will fail. So the second, the late ones, because the other thread updated the value of flag between its load link and store conditional, and thus have to try to acquire the lock again. So that's why this code for int, if no update to asterisk pointer since error to this value, asterisk pointer equals to value, return 1 success, else return 0 failed to update using store conditional. So that's the advantage. You can interrupt both all you want, but those few seconds will matter and will be able to synchronize the update.